All right. I will begin with a word of prayer. So, Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just pray that you be with us today. Help us to understand your creation just a little bit more together. And just pray that students would ask good questions as they think of them, Lord. In your name I pray, Lord Jesus. Amen. So, any questions? Yeah.
Could you work an example of a partial fraction with two words in the bottom of, like, say, x squared plus a, x squared plus b? So I tried to do it, and I got ax plus b over x squared plus cx plus d over x squared. That's a complex roots 5 and 10.
So a partial fraction where you have a product of two, like x squared plus 3 and x squared plus 9, x squared plus 4 or something like that. We could do that. So the question is, how do you integrate something like, what do you want to put upstairs? I'll make it something interesting, relatively interesting, like 2 plus x there. That way it's not entirely trivial. But there's something up there, x squared, let's say plus 9 times x squared. I'm going to be lazy and put a plus 1 down here. That's okay. Is that what you're looking for? Okay, so then the question is, how do you integrate such a thing? And the answer is partial fractions, right? So the partial fractions decomposition for something like this. We have 2 plus x divided by x squared plus 9 times x squared plus 1 is, all right, so here we go. Ax plus b over x squared plus 9 plus cx plus d over x squared plus 1. All right, yep. Well, the only way I can factor these is to use complex, because x squared plus 1 is like x plus I times x minus I. So, it is true. You could write this as, like alpha 1 over x plus 3i plus alpha 2 over x minus 3i plus alpha 3 over x plus I plus alpha 4 over x minus I. That algebra is true, and these alpha 1, alpha 2, alpha 3, alpha 4 would be complex, and then we wouldn't know how to integrate those things. So it doesn't serve our purposes, even though it's true. So for that reason, if it's prime, like x squared plus 9 and x squared plus 1 is, then this is the partial fractions decomposition, right? Because we're interested in integration, right? Okay, so multiply both sides by the denominator, and we get 2 plus x is equal to ax plus b, parentheses, times x squared plus 1, plus cx plus d, times x squared plus 9. Now there's various ways to solve this. I think the easiest way to solve this is actually to use complex arithmetic. Because complex arithmetic, well, let me show you. I haven't showed you this yet, but this is something neat. Now, all right, so the less interesting way to do this would just to be pick 4 different numbers, plug it in. Beep, 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 beep. It gives you 4 equations in A, B, C, D. 4 equations, 4 unknowns. They're linear equations. You could solve them, right? You could use the matrix technique I show in the notes if you wanted, but is there a better way? Well, yes, if we're more clever in our choice of how to create the equations in A, B, C, D, we can make our life easier. Here, basically, if you can think of something that makes these 0, that's really nice. But there's an unexpected aid here. If we put x equals to I, do you guys know what I is? Square root of negative 1, right? So it turns out that these equations are still true when they're thought of as a complex equation. Even though we're interested in a real result, we can do some complex math on the way, right? You've already been doing this since middle school or whatever. Whenever you learn the quadratic equation, you learned that A real problem requires complex arithmetic, right? It has meaning, nevertheless. So, okay, so we get 2 plus I equals to what? Well, AI plus B times I squared plus 1 plus parentheses CI plus D I squared plus 9. All right, so I just plug in I. Then what? Well, this is the beautiful thing about I in this problem is that this is 0 because I squared is minus 1, right? What is I squared plus 9? 8, right? So we've got 2 plus I is equal to, this is 8. So that gives me 8D plus 8CI. Something you should know. A complex equation is simultaneously two real equations. So when you have a complex equation like this, you can equate the real and the imaginary parts. So from this single equation, I get two separate pieces of data. In particular, I get, from the real part, I get 2 is equal to 8D. From the imaginary part, equating the coefficients of I get 1 is equal to 8C. These equations beat the pants off whatever would happen if you just plugged in 4 real numbers into these equations, right? Those are super nice. We now know what C and D are. And if we plug in x equals to 3i, we'll practically be done. So plug in 3i, I get 2 plus 3i. I know what's going to happen this time, right? This piece is going to go to 0 because 3i squared is minus 9. Minus 9 plus 9 is 0. The other piece is going to give me 3ai plus b times, let's see here, 3i quantity squared plus 1, right? And then the other term is 0. And what does that give me? Well, this works out to what? Minus 8, yeah. And so what we have is minus 24 AI minus 8b is equal to 2 plus 3i. And from this single real equation, I can read two complex, single complex equation. I get two real results. This gives me, on the one hand, 2 is equal to minus 24. Excuse me. 2 is equal to what? This part matches that part. So 2 is equal to minus 8b. And 3 is equal to minus 24a. So this is the real part of the equation. This is the imaginary part of the equation. Now we have all we need to integrate, right? Because, lo and behold, this gives us that, let's see here, we got integral of 2 plus x over what I have, x squared plus 9, x squared plus 1 dx. So that's actually apparently, let's see here, click my results. What's my a? I guess I should actually write down over here. What's a equal to? What's that? Negative 1/8, okay. What's b equal to? Negative 1/4 or negative 1/4, right? What's c equal to? 1/8. What's d equal to? 1/4. All right. So what I'm going to do is I'm going to be lazy with the fractions, and I'm going to factor out an eighth. I think if I do that, I can, yeah, I'll just factor out an eighth. And then when I'm integrating, my a is, what was it? Minus 1. So I've got minus x. What was b? 1/4, which is minus 2/8, right? So that makes minus x minus 2 over x squared. Did I do the 9 or the? Yeah, plus 9. And then what? C, so then plus x And the d is 2/8, yeah, so plus 2 over x squared plus 1, all dx. And we can integrate those, right? So actually, let's see here. The x over x squared plus 9, we make a u equals the denominator substitution. And I think that's going to give us minus 1/16 natural log the absolute value of x squared plus 9 minus, oh, fine, I guess I need to write those details out. Actually, can I stop here? Because do you guys know how to go? Do you guys know what to do past here, or do we need to see me do it again? Yeah.
I have a question. So when you first substituted I for x, what happened to the a when you went to when you went down to like c and d?
This is 0.
Oh, because I squared is negative. Okay.
So 0 times something, gone. Just like in the next one, this became 0, and so that was gone.
Yes, sir.
Yeah.
And then when you split into real and imaginary, how does that work? All your like factors with that, or all terms without an I disappear, or vice versa?
So the way real and imaginary works is that whatever's real in the equation has to be equal, and whatever's complex, whatever the coefficient of I is in the equation is equal. Take this for granted when we write something like a plus bi is equal to 7 minus 4i. So if I tell you that, from that you can read a equals 7 and b equals minus 4. That's unambiguous. That's an inevitability. And the same is true for these equations. So I can equate the real part, and I can equate the imaginary part. Yep.
Is that because they're on, like on an x and y graph, you have x variables and y variables, so you can subtract the y variables from each other?
I mean, it's because complex numbers are really points in the plane, if you want to think of it that way, like you're saying, yeah. So 2 points are equal only if they have their x and their y components matching. The y corresponds to the coefficient of I. The x corresponds to like the, well, the real part, and which also happens to be x in my current discussion. I probably need to go through this integral, right? So let me just do that right quick. So there's 2 pieces here, yeah? The one is like 1 over 16, minus 1 over 16 dw over w. And then you've got, minus 1 over 4 integral of dx over x squared plus 9. And then plus, 1/16 integral of du over u, plus 1/4. Oh, well, I don't really need to write this. I'm writing it down just to be symmetrical, let's say, but this we shouldn't. We should know this integral, right? That one's fine. So I'm making a w equals the denominator and a u equals the denominator substitution, right? When I do that, for example, if I let w equal x squared plus 9, that gives me dw is 2x dx, which gives me x dx is in fact 1/2 dw. And that's why I have a 16th out front, and I factored the minus out as well. Similarly, the u pulls a 1/2 out from the du.
Where did the minus 2 come from the substitution?
Here?
The numerator of the dw minus x minus 2.
Oh, no, here. I had an 1/8, and then 1/8 times 2 is 1/16.
The minus x minus 2, not minus 2.
The minus 2 is over here.
Okay.
Yeah. Now, okay, so what we're up against then is minus 1/16 the natural log of x squared plus 9. And I'm gonna do that one last, okay? Plus 1/16 the natural log of x squared plus 1 plus 1/4 inverse tangent of x. And then we still have that x squared plus 9 integral to contend with. How do you do that one? I mean, there are various methods. Oh, can you move the camera here? Thanks. So I think the natural way to do that one would be to let x equals to, what, 3, do we want a tangent? Do we want to, I think we want tangent theta, right? 3 tangent theta? Because then x squared plus 9 is what? 9 secant squared theta. And dx is 3 secant squared theta d theta. And so this piece integrates then to, like, this piece is integral of actually a quarter out front, right? There's a minus 1/4 out front. But the dx is 3 secant squared theta d theta. And the denominator is a 9 secant squared theta. So the secant squared thetas cancel. You're just left with, you know, minus 1/12, well, minus theta over 12. So that's why the next term is minus 1/12 inverse tangent of x over 3 plus a constant. So, yeah, there you go. Yep.
If you possibly make x equal to like 3 here, and then factor on the 9 and just do tangent, would that be
Make x equal to what?
like 3b or something? So it's squared to 9b squared. So you can make it factor on the 9 and you just take the arctangent.
Oh yeah, you could factor a 9 out and then make like a v equals x over 3 substitution to just change it. Yeah, I mean you could do that. Yeah, there are other ways to do this. I think trig substitution is easy. Now, although that reminds me, Dr. Sprano probably disagrees with me because he thinks that that integral, and I kind of see why he says this. He argues that this kind of integral is basic and something you should just know without doing further work. You should just have this memorized because he has it on his list of things that we have memorized from Calculus 1. So here's Dr. Sprano's things we have memorized from Calculus 1, or, not to put words in Dr. Sprano's mouth, or we can derive, I'm sure he would say, right, from Calculus 1. So here is a handy-dandy sheet of things that you may or may not know, but it would be super helpful to you as a means of not making Calculus 2 problems more difficult than they are, which is difficult.
Is written on?
What's that?
The matter is written on.
Oh, yeah, thanks. I'll take that one back. I wrote on that one. Sorry. Do I need another one then?
Probably.
Yeah. So anyway, this is, now, in some sense, this is a very silly homework assignment because it just has the integrals. It doesn't have the answers. So, but it's worth writing the answers on this sheet because this is kind of, you know, sorry, it's been a little bit since I've taught Calculus 2. If I was more with it, I probably would have given you this like day 1. I meant to give it to you last class, and I just forgot. But all right. Any other questions? Did we pass around the attendance sheet? That's a very good question. So, in fact, because we get to check 2 boxes today if you were here yesterday, yeah? So let's see here. Yesterday and today. Here you go. Thank you, sir. All right, so I did that problem that that I put on the board yesterday. I did my homework, and that one's a doozy. Yep.
So I have a question.
Go for it.
When you did the trig substitution, you said x was 3 tangent theta, and then you said x squared plus 9 was 9 secant squared theta.
Yep.
Why'd you say that x squared was 9 secant squared?
Algebra. Like, because this gives us 3 tangent squared theta, but 3 squared, right? So it's 9 times tangent squared theta plus 1. Tangent squared theta plus 1 is secant squared. So it's always this algebra, like it's that algebra every time. I wrote the algebra in the, when I wrote it up here on the board the first time, like it continually comes back every time, that algebra. Okay, so any other questions? I mean, feel free. Yeah.
The second integral, we moved over to the right to figure it out and then moved it back to the end.
Yeah, just, yep. So, yep, go for it.
When you're finding the coefficients like A, B, C, D,
Mm-hmm.
what's the difference between finding AX plus B versus just A over something plus B over something?
The difference is the denominator. When the denominator, there's three different things that can happen for the denominator, right? If we're talking about a quadratic denominator, it's either we're talking about a denominator like right, or we're talking about something like this, or we're talking about something like these are different because the denominator in the first one factors over the reals, the second one's a repeated root, the third one's a prime. Each one of these has a different approach. This one, we do this. This one, we do this. And this one, I complete the square. So I do something like this. And the reason I do what I do is that my goal is integration, right? So I know what I've written on the right-hand side, we can integrate easily. And that's why I don't do something else. Although other things might be logically possible. Yeah.
What if we have, so we have 2 plus x over x cubed plus 9.
Whoa, just a second. 2x plus what?
I was just 2 plus x, but 2x plus.
Oh, 2 plus x over what?
X cubed plus 1.
X cubed plus 1.
Not x cubed plus 1 plus 9. So
X cubed plus 9? Oh, okay, good. So that is 2 plus x over, let's see here. I can plug in the cube root of minus 9, and that makes that 0. So by the factor theorem, that's x minus the cube root of 9 times x squared plus something plus, well, minus rather, the cube root of 9 squared. Now, what exactly that is, I could fall back on the, remember the cube formula? So like a cubed plus b cubed is what is it? It's a minus b times a squared plus ab minus b squared, maybe? Am I right or am I wrong? I might be wrong. I don't know. Let's find out. So I get my b cubed back, I get my a cubed back, and I need the middle stuff to cancel out if I remember this identity correctly. So that gives me an a squared b. This gives me minus ba squared. That's good. They'd be canceling. And then ab squared minus ab squared and a. Rats. Maybe that's a minus in the middle. I always have to battle the signs of this thing when I try to remember it. It's 2 positives? 2 positives, okay. Thank you. So I was supposed to put,
I think it's like a plus b and then a squared.
oh, I'm sorry, I'm an idiot. I'm getting confused about the, not you. I'm an idiot. So I was supposed to put a plus cube root of 9 here. The reason for that is if I plug in x equals minus cube root of 9, that makes this 0. So it's the old, if 2 makes it 0, x minus 2 is a factor issue, just in this more complicated setting for me. But anyway, so what were you saying? I'm sorry. Is this better? So I'm supposed to have a, you guys are saying I'm supposed to have a plus b? So now we're thinking a plus b and minus ab over here? Anyway, my point is there is such an identity, and if you sort through that, you can figure out, what the middle term here, which I believe is just, let's see here, so it's like this, and so I'm think we just got plus the cube root of 9 x in here, and there's a minus there. And then what can you tell me about the quadratic? X cubed plus 9, what's the graph of that look like, guys? The y-intercept is 9. It looks like this. Yes? There's y equals x cubed plus 9. So how many real zeros does y equals x cubed plus 9 have? Just one, right? What's that tell you? That tells you the other two are complex, right? Which means, by consequence, this is a prime polynomial. Right? I could complete the square on it and make it pretty. Yeah? But just to the point, this has partial fractions decomposition. A over x plus cube root of 9 plus bx plus c. If you want to be lazy and not, the thing I did, I could make it prettier, but I think let me not, spend too much more class time on this one. That would be the partial fractions decomposition for this. The larger part of the story is that there's a fundamental theorem of algebra, and any polynomial can be factored into a product of linear factors possibly repeated or prime quadratics possibly repeated. So it suffices to explain how to do partial fractions for denominators which are products of either linear or quadratic factors or possibly repeated. That said, I'm not saying that actually finding those factors is an easy business. It's not, right? If you give me a 10th order polynomial and say factor it, I'm going to be like, give me some money, right? Or a computer. I mean, that's hard. Yeah.
So why is it then, for the middle example, why is it x minus 2 then plus x minus 2 squared? Like, why? Because wouldn't that be like a third degree, if you like multiply them all out, is that 3 degrees or why?
Well, here's the thing. If I have a over x minus c plus b over x minus c quantity squared, and I make a common denominator of that, that gives me a times x minus c plus b over x minus c squared, which is, of course, ax plus b minus ac over x minus c squared. So you have to ask yourself the question, if I start with an arbitrary thing of this form, what does it go back to? The answer is, by this algebra in reverse, something like this plus something like that. You have to have the square. You can't just repeat 1 over, you can't just do a over x minus c and then plus b over x minus c again. Like, it's not sufficiently general. Now, you could do this. You could do like a times x minus c plus b over x minus c squared. That is true, but it's also useless. Well, it's not useless, but it's not as useful as this, because this we know how to integrate. So we do that. Logically speaking, it's equivalent to this. It's the same flexibility. Yep.
So I know when you have two denominators, you cross multiply. How would you do it whenever you have like 3 or 4?
It's the same. It's the same. So, if I have a over x minus c plus b over x minus c squared plus apparently d over x minus c cubed, how would I make a common denominator there? Well, I would do a times x minus c squared plus b times x minus c plus d all over the quantity x minus c cubed. And you see, up to a choice of like relabeling constants, this is the same as something like alpha 1 plus alpha 2x plus alpha 3 x squared over x minus c squared. So because for arbitrary choices of alpha 1, alpha 2, alpha 3, in general, we can get back to things of this arbitrary form. We must, because we don't know ahead of time how the algebra works out, put down A, B, C of this form when we come up against something of this form in order to say how it rips apart into basic rational functions. Like that, that's just how it is. So you guys are just continually asking me why the proof at the end of my integration techniques section is true. Like, this is what the proof is that the partial fractions I keep referring to works in general for things of the form that's intended. But these are good questions you're asking, and natural questions, but you just have to understand that there is a fundamental difference between distinct factors, repeated factor, and prime factor. We have to treat those separately, and the integrations are likewise different, yeah.
What if there's like 3 distinct factors, you still cross multiply the same with all 3?
3 distinct factors.
So like you had like 1 over x minus 2 times x plus 3. What if there's an alpha 1?
So you had like a over x minus 1 plus b over x minus 2 plus c over x minus 3. That's a times x minus 2 times x minus 3 plus b times x minus 1 times x minus 3 plus c times x minus 1, x minus 2, all divided by x minus 1, x minus 2, x minus 3.
Which the denominator would divide out anyways, so it would just be the numerator dealing with.
Well, yes, I mean, we can undo what I just did, but the point is, generically speaking, if you have, so like if you just multiply this out and you think about it, really it's the same as have something generically of the form alpha 1 plus alpha 2x plus alpha 3x squared divided by the product of x minus 1, x minus 2, x minus 3. So the point is, if we come up against something like this, it's sufficient to put down this as our general template for how it breaks up, because we can do the algebra in reverse. Now you have to believe me that the formulas that I get for the coefficients alpha 1, alpha 2, alpha 3 are sufficiently general that it covers all possible cases. And that's what the proof at the end of my integration techniques section is all about, actually. So like, what's the formula for alpha 3? Alpha 3 would be, 6a plus 3b plus 2c, right? Alpha 2, what would it be? Multiply this out, I get the coefficients of x, yeah? So coefficients of x here give me a minus 5a. Coefficients of x here give me a minus 4b. Coefficients of x here give me a minus 3c. What's alpha 1 equal to? Alpha 1 is the constant terms here, which would be 6a plus 3b plus 2c, right? So it boils down to, can I solve for arbitrary, can I get any alpha 1, alpha 2, alpha 3 for choices of a, b, and c? And the answer is yeah. It does that. So I'm long past the original adapter for this thing, so this is an aftermarket one, which is kind of sketchy. But hey, it's not been intermittent for a while, so that's good. So like, how do I know for sure? How do I know for sure that for any choice of alpha 1, alpha 2, alpha 3, I can find a, b, and c to make this so? It's equivalent to the question of, does this equation, system of 3 equations, 3 unknowns, does this have a unique solution, right, for arbitrary alpha 1, alpha 2, alpha 3? And the answer is yes, because if you look at this as a matrix, that matrix has non-zero determinant, which means this is an invertible matrix which has a unique solution. And I could work that out, but we don't have linear algebra, so that would be kind of bad. But ultimately, this technique rests on a complicated question about systems of linear equations relating coefficients of sums, which is the proof at the end of my integration techniques. So I don't think I'm answering the question you're asking, though. You're really just asking what's the difference between these. And the answer to there is just the denominator has a different factorization. That's it. And keep in mind our goal, which is integration.
What were the 3 factors called? It was being.
I'm sorry?
What were the 3 factors that you called over here?
Over here?
On the middle board. You said there's 3 different.
Oh, so this is the distinct real factors, right? A repeated real factor, and then this is a prime polynomial, right? It doesn't have a real 0. You have graphs of quadratics, right? They either cross the x-axis 2 places, they bounce off the x-axis, or they don't cross the x-axis at all, if you just look at the graph of the denominator. Man, Dr. Sprano told me something really interesting before class. I really want to go work it, but I really shouldn't. All right. All right, so let's work another example, yeah? And so I'm going to resist the temptation I have to share with you my homework I did last night, which took me considerable time. That problem that I left on the board yesterday is pretty difficult. It has the denominator's quartic, and like the partial fractions is interesting. The integration after that's interesting. It's just all interesting. So it's going to take me like a half hour to present that problem at least. So in the interest of making the best use of the last 15 minutes, let's work a problem which is of more moderate difficulty, all right? And so here we go. Because this will illustrate, so I showed you, listen, they're basically 3 or 4 main ideas for solving the equations for the ABCDs. The one is to plug the roots in, right? The other, like I just showed you over there, is if it's prime, it's often helpful to plug in a complex number because that gives us really nice equations. But there is yet another thing to do, which is convenient for when we have like a repeated root. And to really drive it home, let's look at a three-peated case, something like this. Suppose we're up against the integral of 3x plus, let's say 3x squared plus 2x plus 1 over, I'll make it relatively simple, x minus 1 cubed. And I really, just for the sake of, no, okay, so there's something I wanted to talk about today, and we got off on other tangents, but you understand if we had something like, I just want to say this, and this is just a throwaway comment to help you with homework, yeah? But if I had something like this, 3x plus 2, 2x minus 7, it's perfectly fine. You can do the partial fractions like this, all right? There is some flexibility in the formatting. Certainly you can do this. I would do this. I would still consider that partial fractions, okay? I don't want to be so dogmatic that you have to write it as a product of factors where the coefficient of x is 1. Because it's just, so just want to say that. Now that I got that out of my system, what's the partial fractions for the one I've just posed?
A over x equals 1 plus b over x equals 1 squared.
So you said, oops, not plus, equals what? A over what?
X equals 1.
X, yeah, x minus 1, and then b over
X equals 1 squared.
squared.
And
I would put a minus there, I'm dummy. C over what?
X equals 1 cubed.
Okay. All right, so let's do this thing. So first order of business, multiply by the denominator, right? So we get, great questions today, guys. It's good to ask questions. All right, and I'm going to call that thing Pac-Man. All right, so what I like to do is I like to feed Pac-Man. Oh, man. Nom, nom, nom. 1. All right, so I get 3 plus 2 plus 1 equals to what? Yeah, a times 0 plus b times 0 plus c, right? So therefore c equals to 6, right? then what to do next. Now here's something I haven't showed you before. But for a repeated root problem, a lot of times, a nice thing to do is simply to differentiate the equation you're dealing with. So d Pac-Man, or if you like Pac-Man prime, I'll do d Pac-Man. Nom nom nom. dx. Feed it 1. All right, so, well, first of all, what's d Pac-Man dx? It's 6x plus 2 is equal to, all right, how do we differentiate x minus 1 squared? It's twice x minus 1, right? Derivative of this is just b, right? C differentiates, it's gone. That's really nice, there's no c. I mean, we already knew c, but hey, it's gone now anyway. And now let's feed it Pac-Man prime 1, nom nom nom, equal to 8. 2a times 0 plus b. So therefore b equals to 8. Now if you don't know this trick, right, you can just plug numbers in and you'll get 3 equations and 3 unknowns, and you probably can solve them still, right? But this is easier. And then what's Pac-Man prime prime? Prime prime. 6 equal to 2a, yeah? So apparently a is equal to 3. So lo and behold, we have found the partial fractions decomposition. And can you guys see if I write down here? I don't know. Poor planning. I should have put this over here. All right, well, I'm going to foolishly, I'm going to say this is equal to, let me put the answer I just found up at the top of the board if you guys don't mind. So we're looking actually at the integral of what? A was 3, so we've got 3 over x minus 1. B was 8, so plus 8 over x minus 1 squared. And then plus 6 over x minus 1 cubed. Any questions about this before I erase at the top? Okay. And so, don't forget my dx, don't want to lose my 10 decipoints. And so we can integrate those, yeah? We make a w equals x minus 1 substitution, right? And so essentially, I mean, I won't even write it down. The integral here is 3 natural log the absolute value of x minus 1 minus 8 over x minus 1 minus 12 over x minus 1 squared. I think. Oh, wait a minute, my bad. 6 divided by 2, right? Which is what? Not 12, dummy. Me, not you. 3, right? And then just to check, you know, I always, when I do the integration like this, I try to make it, just take a second to differentiate it to make sure I'm right. If I differentiate the reciprocal, that's the minus 1 power. So I get minus 1, which is minus 2. The minus cancels, so I get a plus 8 over x minus 1 squared. If I differentiate this, it's the minus 2 power. So minus 3 times minus 2 is plus 6. And I reduce the power by 1, which is 3. So there you go. And that is how we integrate that sort of thing. Yes, sir?
So if you set up the code for your partial fractions wrong, how will you know that it's not going to work?
Your equations won't be solvable. You'll get stuff like 0 equals 1. You'll be driven to make variables, the a, b, c are constants. You ever find yourself writing something like a equals to x? You're in a bad place. Okay, so like don't do that. But I will see that, like the prophecy, it will be true. Someone here will write a equals x on the test, yes.
So you're supposed to take...
Let me be a false prophet, please, yes.
You're supposed to take the derivative of the numerator.
Wait a minute. There's kind of severe consequences for them. I shouldn't do that. It's going.
You're you're supposed to take the derivative of the numerator when you're solving for like A, B, and C, like after each step? Or could you have done that without taking the derivative?
Oh, you're talking about what I'm erasing.
Yes.
So the issue is that when you have the repeated root, if you differentiate it, it gets you a new equation. Like this is an identity. If an identity is true for all x, we can differentiate it. It's still a true identity, right? Because it's a polynomial identity, which means it's differentiable. So like differentiating it gets me new identities which are still true, and they're also convenient because I can still plug in that root which was repeated, and it gives me something interesting, right? If I plug 1 repeatedly into the original Pac-Man identity, I just get the same thing back again. But the derivative, on the other hand, gives me a genuinely new equation.
And gets rid of that C constant, right?
Yeah, it gets rid of the C constant too. Yeah.
And it also makes B a constant instead of making x.
Yes, it's just, it's all around good. Now, this trick becomes less awesome when you have a mixture of a repeated root and something else. Just generically speaking, when you have 2 of these different 3 cases and they're mixed together, the equations get interlinked and you just have to deal with the difficulty of it. I mean, there's just solving systems of equations here. It's just, they're not bad, right? They're not as bad as the equations we just make up in linear algebra, but they are there and you have to solve them, right? 3 equations, 3 unknowns is not on 4 equations, 4 unknowns. It happens in these problems, yeah. There's really no limit on the number of equations and unknowns. It just depends on the degree of the denominator. So let me show you something else before we forget here. What if we want to integrate secant theta? Well, you guys know, right? We do natural log of the absolute value of secant plus tangent, right? Hopefully we've kind of learned that by now, right? But now we have means to derive it, actually. Check this out. So I just need to be a little bit creative and say, well, okay, so that's really cosine theta squared over cosine theta, yeah? Which is the integral of cosine theta d theta over 1 minus sine squared theta. Which is, oh, by the way, du over 1 minus u squared. And 1 minus u squared is 1 over 1 minus u, 1 plus u, times 1 minus u, which is like, you know, a over 1 minus u plus b over 1 plus u, 1 minus u. Which, if you tilt your head and squint, you can see that a and b should be, what are they? Let's see here, what do I got? I put u equals to 1. So b is a half. And I think a is equal to what? Minus a half. All right, so I get, you know, 1/2, 1 over 1 minus u, plus 1 over, minus 1 over 1 plus u, I think. Which is 1/2, you know, minus 1/2 natural log absolute value of 1 minus u plus the natural log the absolute value of 1 plus u, I think, if I have not messed up a sign. Which is, yeah?
If it was a times 1 minus u, and we were substituting at minus 1, would it be 1 equals 2a instead of 1 equals minus 2a?
Yeah.
What I done?
Where you substituted negative 1 a for b.
No, we're out of time. So, well, anyway, let's just leave it at this and just say you can finish this and derive the formula. It won't give you exactly the same formula we know from the u substitution, but hey, we could derive this now if we wanted to. Have a good weekend, you guys. Yeah.
Isn't this going to be on the quiz on Tuesday?
Will trig substitution and integration by parts be on the quiz Tuesday? Yeah. Partial fractions could be on the quiz Tuesday. Yep, that's true.